Let's suppose we have a maze and we want to find the exit. Furthermore, we want to find the most efficient way. I'm gonna show how to do that with a framework called reinforcement learning. Let's briefly go through. The scheme is known as a collaboration between the environment and the agent. Agent interacts with the environment by pushing actions. Environment does a certain activity and sends the data back to the agent. And this loop goes on until the goal is achieved. What makes it famous is that the model is abstract and fits various of tasks. But how does it pave desired path? So far there are a lot of description of what's going on there, but almost all of them are full of tech nomenclature. Some of them you can find in the reference at the description, but I didn't find a clear visualization, particularly how the system learns nonlinear steps, which was the most mysterious for me. Let's define our environment. At first, the task is supposed to be in a readable format, so that it can be fed to the agent. We should define our boundaries of what is under control, our space of actions, and consequences of our actions, our space of states. For instance, we are in a certain location, let's call it state 1. Based on current state, we select an action, move to the left, and the next location that the point comes to is state 2. In general, there might be a chain with actions and transitions. We don't have to model the whole chain like this, I just wanted to show how the agent observes the environment. Next, each state should have a reward. Since we aren't in the finish, we will feed the agent a negative reward, and only at the end we will feed a positive one. The reward is like a navigation system. We inform our agent when we are in the desired state, and the agent looks for the best combination of actions to feed the environment. Now let's go to agent side. The agent requires a much more workforce. Many approaches are already predefined. I didn't classify them from scratch, as Google already has them. Instead, I tried to generalize all them, and the things comes down to 3 common paths. The path that updates a memory or waits in neural nets, the memory storage, and the path that chooses the value from that storage. Back to our approaches, I will say shortly that there is no best approach to solve all kinds of tasks, since each of them has its own pros and cons. I will use one of them, it's relatively simple and it's called the tabular variation of Q-learning. The tabular means that our experience memory is a table. Number of rows is equal to actions, and number of columns is equal to states. The agent observes the table on each step in order to select next action. The goal of the technique is to set the table in a certain condition, when action is being chosen properly during all the path. And that means the agent knows how to solve the maze. The values in the table are altering continuously during interaction with the environment. It reminds the process of analyzing the result of the performed action. Let's see how it works. Since we don't have any experience at the beginning, we initialize the table with zeros. In the maze, we can see that we started from state 1. In order to calculate our values, we should perform an action first. According to a certain rule, agent selects the next action. The rule is called policy. We use a greedy policy. It means that agent selects an action with the maximum value. Currently we have same numbers. We select a random among them. It's sent to environment. The environment gives us next state and reward. Now we are on new state, state 2. Take experience value for previous state, then take maximum value for current state, add received reward, and we've got the best experience we could gather making move to the left from state 1. Alter the previous state value towards our best experience by small step. And the last, put new value back to the table. Since the best experience is also redefining continuously, it could be mistaken, hence we update it gradually. Whole process could be described like agent memorized a small amount of experience of transition from previous state 1 to current state 2. One more time. This time policy selects to move the point down, and our environment doesn't make any changes. That's why we are still in the same state. The increase or decrease of the experience depends on two values, the reward and the experience from the next state. The agent is heavily oriented towards positive reward, while the experience memory doesn't saturate it enough. In course of time, the influence of memory grows, and it causes the agent to pay more attention on own experience than a short-term reward. Performing that iteratively, we would have a spread of values across all states. In the first couple trials, the values of the table would move in the wrong direction, but when the agent reaches the finish, it corrects during the desired path. We could describe that as at the start the agent has no clue how to behave, and does it randomly until it has got a positive reward. Our agent repeats the process on each step until it selects actions without mistakes. Here is the experience table that I've got on the end. And this is how our model absorbs experience. As you may notice, the trick is not memorizing the path, instead it keeps in memory only experience values for each state and its corresponding actions. What happens if we have several ways to pass the maze? Our previous algorithm will find the way from any maze, but we want to have the most efficient way. The choice that we make relies on the experience table, and the action to the left has the highest value. Since we have two ways, the alternative path will be thrown from the agent's attention. There are several methods to solve that. We can play around with the initial values or decrease reward at the finish. It would work, but it's not a universal approach for each maze. The most common approach is to allow irrational behavior for our agent. Adding a pinch of randomness helps the agent to explore new roads on each state. Now, we have a random value which is the policy manager, whether to choose maximum action or a random one. In this case, we increase the chance to explore the move to the right, which could be a shorter path. In short term, it takes more time to learn the whole map, but in long term, we will have a more efficient result. That compromise is known as the exploration versus exploitation problem. Putting it all together, we have a model that could have solved the maze. The last thing I wanted to mention is that it's a simplified version. The process I call to learn is formally called to approximate the function. I also skipped the discount rate and learning rate constants just to make reinforcement learning more intuitive. The full update rule function is here, and an example of usage on different problems you can find in the description. That's it. I hope that it was useful. If you have questions, leave a comment.